Hello, and we are live in the virtual jug. And it's me, Ivan, and maybe you've seen me in the VJUG book reading club, but now it's my first session as VJUG host. If you want to join the discussion, you can go to our VJUG Slack channel. There's a live session channel there, and if you want to go and find the Slack channel, you can go to the VJUG website. Today, our session is about continuous profiling in production, and we have the virtual jug veteran, I should say, Richard. It's his maybe fifth or sixth presentation today with virtual jug, as well as Sadik. So without further delay, I am going to give, please guys, present yourselves.
Thank you very much, Ivan. It's lovely to be here.
Bye.
Okay, so maybe, we can start.
Okay.
And share your screen.
I'll give you some slides shared. Lovely. We happy to go?
Yeah, go on.
Brilliant. Well, so as I say, my name is Richard.
My name's Sadik.
And we're going to be talking about continuous profiling in production. So we're going to cover a bunch of different topics in this talk. And we together run a startup called Option that offers a great production profiling solution. But, our talk isn't necessarily about that tool itself. It's more about the bigger kind of methodology and approaches that you have with production profiling. So for a start, we're going to talk about why tools like this matter, why they're important and useful to your organization. Then we're going to talk a little bit about the distinction between development and production. And then we're going to talk about, how profiling itself differs from other monitoring concepts. And then we're going to talk a little bit about how you can do production profiling with really low overhead, because we frequently encounter people who say, look, we love profiling, we're a big fan of it, but we just can't do it in a production setting because it slows the system down too much. So we're going to talk through a bit of the more deep dive technical aspects of how you can do that. But first, let's have a look at why these things actually matter. What's the important thing that we really care about here? Well, when you think about performance as a kind of characteristic or a quality of your software, the first thing you might think about is your known knowns. Okay, so these are the things that you know are relevant to performance, and also you kind of know the answer to those kind of things. So for example, you know that reading some data out of memory is always going to be faster than reading it out of a disk. Okay, you know properties like that. You can reason ahead of time without understanding anything about the specifics of your system about, say, a couple of algorithms, which one's going to be faster as the size of your data set scales up. So those are your kind of known unknowns, things you can think about in development time. As you kind of put things into a production setting, as you start to deploy your software and get more and more users, you might start thinking about known unknowns. So these are things which you can understand of as being a problem, but you don't necessarily know what the answer is. So for example, we said earlier, you know that your RAM is faster than your disk, but you don't necessarily know what the ratio between the speeds of those two things is. You don't necessarily know exactly what the latency of a page load is going to be until you really go ahead and test it and see it. And known unknowns are a kind of performance characteristic that people often solve with a lot of monitoring and metrics. So they measure things that they know about ahead of time, and then they can understand what the real values of those things are, the known unknowns. But it's the third category of problem that can often be the biggest issue for people in a real production setting. And that is the unknown unknowns. So these are things that totally blindside you out of nowhere. Things where you don't know that there'll be a problem ahead of time, and you don't know what the value is, or what the concrete aspect of this problem is either. So for example, maybe you've got some really nice fancy parallel sorting algorithm that you put into production into your system, Well, the unknown in that case might be that it's really just running at the performance of a single thread, because you're doing a bunch of synchronous logging, and all your different threads there are all waiting on a big lock in your logging subsystem that's slowing you down and ruining all the parallelism. That kind of thing is an unknown that you just don't know what that problem is. And that's the thing where performance tools really come into their own. That's the area where continuous profiling especially comes into its own as a way that it can help you solve problems that you didn't know you had until they hit you right in the face. So, kind of said why we care about these kind of things, but the first approach a lot of developers have for testing software is testing it in a development setting, right? But why can't we just apply this to performance as a character? Why can't we do performance testing in development? Sadiq, what do you think about that?
All right, so we're gonna go over now why, from a performance point of view, development isn't production. And when we say development here, we mean stages before production. So this could be development, this could be QA, this could even be test. And why, from a performance point of view, these are not representative of production. Because taking a step back, at the end of the day, our goal here is not to make our development environment run quicker. Our goal is to make production run quicker and to remove bottlenecks in production. So if we're only seeing bottlenecks that actually manifest themselves in development, then we're not really achieving our goal here. So why do people do performance testing in development? Well, for one, it's just easier, right? As a developer, you may not actually have access to production. In many companies, there are walls between developers and operations, and there might be legal reasons why that's necessary. But also the tooling tends to often be desktop-based. So we're quite used to actually firing up some tooling that connects to a local JVM and then gives us the information we need in a nice user interface. And so that makes doing performance testing development much easier. But as we'll see over the next few slides, it's not representative of our production environment, which is the goal here. So the next thing is, to start with, is that development is not representative of production from a hardware point of view. Very few developers I know actually work on the same hardware as will actually be running in production. Most developers have a laptop that has maybe 2, or if you're lucky, 4 cores, maybe 8, 16 gigabytes of RAM, and it's primarily optimized for power consumption. So it's optimized for short bursts, but to actually give a low resting power usage. Whereas server hardware is designed for throughput. So you might not be running in such a low power environment. You might have SSDs that are optimized for high IOPS, high throughput. You might have 24 or 32 cores versus the 2 or 4 on your laptop. And when the hardware changes, it causes a shift in where bottlenecks manifest. So for example, if you have a 2 or a 4 core processor in your laptop and you have a 32 core processor in your server, you're going to see very different concurrency or lock related problems on a 32 core processor than you would on your 2 or 4 core. You may never hit some of the race conditions you actually hit in a server environment. Likewise, if you have, say, server grade enterprise SSDs that are able to do millions of IOPS, you'll notice a shift away from IO related bottlenecks to CPU bottlenecks that might not manifest themselves in a development environment. So if you're not testing on the same hardware, you may not actually be seeing the same bottlenecks.
So you're saying even if the production hardware is faster than development environment, it's still not good enough to test in development environment?
Correct.
What about software?
Well, the next thing is unrepresentative software, right? So in many of the companies I've worked with recently, the developers and or development environment and servers actually don't even run the same operating system. So often development happens on Macs and production might be on Linux. But as we saw, even if you're running the same operating system, as we saw from the recent Spectre and Meltdown mitigations, even the same operating system between different versions, so Spectre and Meltdown, the mitigations that were applied for different kernel versions had dramatically different performance. So even if you're running the same operating system but with a different version of the kernel, you may have noticed different performance in development than you actually did in production. But between operating systems, the cost of syscalls, the libraries that are available, it creates a very unrepresentative environment of what production actually does.
As we all know, though, 2019, year of Linux on the desktop. So this problem's going to go away, right?
Yes. Yes. Not to mention also that servers tend to run stable, long supported versions of software. So even if you're running Linux on both, we tend to say maybe you run Ubuntu or Fedora on your laptop, but you may have, say, CentOS or Red Hat Enterprise running on your servers. And they have very different versions of libraries between the two, and that can lead to dramatic performance differences.
Very true. And if you don't think different OS versions result in different performance characteristics, you should check out the Windows Patch Tuesday update that happened at the end of May 2018, where the UDP throughput performance dropped by 40%, just as a result of one of those Spectrum meltdown security patches. Huge.
Sure. And then the next thing is to test in development or pre-production environment, you need some way of exercising that environment so it actually can mimic production. And it is incredibly hard to actually do that. So you can start creating load testing workloads simply. So you can say, okay, well, and there are plenty of questions that you need to answer in order to create those. So first would be, what is the distribution of requests across my endpoints? Well, that's normally pretty easy to answer. But then it's more complicated things like, what is the distribution of requests for a given endpoint between hot data and cold data? Data might have my cache or it might not. That's a lot harder to answer, especially if you're just recording production traffic. And then it's things like, what are the interdependence between the requests to certain endpoints or certain parts of my system? So a while back, I actually worked with a company where we had a problem that a misbehaving SDK would actually hit our API, hit 3 different endpoints on our API at the same time. And those 3 endpoints needed to mutate the same data. So you can imagine that actually we hit contention to actually access and write that data, something that you never would have actually thought about beforehand. Like Richard said, an unknown, the kind of thing that's very difficult to actually recreate with a workload you run against an environment that's just not production. And then the last wildcard we actually have is the JVM. So the JVM hotspot actually does what's called adaptive optimization. So it optimizes the code that's running depending on how it's actually being exercised. So if you're not able to actually exercise the JVM in exactly the same way that production is, then you may be optimizing for some completely different set of performance problems. Hotspot in production may have optimized the code in a completely different way to how it optimizes it in your development environment or your test environment.
I saw quite an interesting example of this where someone was switching from Java 7 to Java 8 with their production system, and they got a 10-fold slowdown moving to Java 8 from Java 7. And that seemed crazy. It was not across the whole system, just across one particularly tight-looped computational kernel part of it. And what had actually happened there was the default setting for how the JIT compiler works had switched from server mode to tiered mode compilation. And the tiered mode compilation had got some methods stuck in a part where they were not properly optimized. So just switching the dash server flag ended up giving that guy his 10-fold speed up back up again. Sometimes these JVM optimizations can be a little bit brittle, something you can't necessarily always assume will be the same.
So the last, so essentially when it comes to production performance profiling, don't do it in development. The dog looks cool, but he has no idea what he's doing.
No, that dog really doesn't know what he's doing. Cool. Let's talk a little bit about profiling and monitoring for a while. So when people look at performance problems in production, or understanding their performance of their system in production, they often immediately jump to these kind of monitoring tools that exist out there, and they can give you a variety of different kinds of information out of your production system. The first type of information you can get out of them is basic ambient passive system metrics. So what these things are is like a pre-configured numerical measure, so a number that you get periodically coming out of your system. So for example, they could tell you how much of your CPU is being used in a given time period, and then you can use a time series query engine, database, graphing system to plot these kind of metrics and see how they come out of your system. A lot of software out there will give you these kind of system metrics, and they can be really useful, right? They can narrow down a whole different class of problems or show you a specific bottleneck or a specific thing. They're also really cheap to acquire. So when I say cheap, I don't mean the pound or dollar cost or euro cost. I mean the cost in terms of computational overhead. How much overhead? How much of your CPU do you need to use to get this information out? And system metrics are a really, really computationally cheap piece of information that you can get out. So really useful. But CPU metrics can sometimes not be the whole answer to your situation. Have you ever been on one of these things, Sadiq, a murder mystery weekend?
Yes, unfortunately.
I've never been on a real world murder mystery weekend, you know, where you get the Hercule Poirot thing and you go around from person to person going, are you the murderer? Are you the murderer? Are you the criminal? Whatever's going on there. But I've definitely been through a few of these in performance terms, right? You start looking at the different metrics in your system and you go, is this the root cause of the problem? Is this the root cause of the problem? Is this the root cause of the problem? And it can take you a while, unless you're as smart as a Poirot or a Sherlock Holmes. You just have to go through there systematically, just looking at everyone in the room until you find the guilty party. Yeah, murder mystery weekends, not as fun as they look. So, logging. Logging is another piece of information that you can get out of a production system. So by logging, we mean, you know, recording some arbitrary event from the system being monitored and then being able to look up at that log, query it, see what was going on at the time. So log4j, slf4j, logback, regular Java logging libraries can be used as a performance diagnostic tool. They can be used to log times of specific events coming out of your system. Now, that has a couple of different downsides. Firstly, it's often manual work to add in that logging time. Secondly, unless you're aggregating all those logs into some sophisticated system that you then have to manage or either pay for someone to host for you, it can be hard to find the specific information, especially at scale, out of this event log. And thirdly, it rapidly becomes quite computationally expensive to process logging information. Things like log4j, slf4j, logback. These can often become performance bottlenecks for your system very rapidly. Some logs are absolutely incredibly useful for understanding system performance. GC logs and GC events, that's a different kind of logging, but also fits into the same category as well. It's very useful to understand what's going on there. So one approach that people take as well, especially in the APM space or the application performance monitoring space, is coarse-grained instrumentation. So when we say instrumentation, what we mean is take some little block of code within your application, measure the time at the start, measure the time at the end, subtract the former from the latter, and then you can calculate the time it took to do a certain little body of code. Now, in general, APM tools don't instrument all of your application because the overhead for that would be too high. They just give you coarse-grained information. So, for example, they can tell you how much time you spent within the control layer of your application, or how much time did your SQL queries take, kind of big coarse-grained operations. This is much more useful than just seeing metrics on their own, as it's a lot more detailed information, and it can also be a lot more actionable. You don't necessarily have to go through that big murder mystery diagnosis step. You can just see much more clearly what precisely is going on there. But the more and more detailed your instrumentation gets, the more computationally expensive it is, the more the overhead is of that instrumentation. So what about production profiling? Well, production profiling is perhaps a different way that we can think of for getting information about your performance out of your production system, measuring your production system. So by profiling, we basically mean tell me what is using a certain resource, what within the application is using up some certain resource. So which methods use up CPU time, which lines of code allocate the most objects, where your CPU cache misses from. I mean, that's a more esoteric type of profile, but again, it's about tying a bit of your code base back to the resource, to the usage of a resource in production, be it CPU, memory, more fine-grained things than that. Now, profiling is automatic, which is a great win over something like manually adding logging instrumentation and manually adding timers and timing into your system. Okay, as it means you can just get information out of the box really quick. It can be cheap, as in computationally cheap. So it can be done with very, very, very low overhead, but most profilers will be just too high an overhead. If you attach JVisual VM or something like that to production, you're entering a world of pain. The other reason why production profiling is a really useful thing to think about as comparison with instrumentation comes back to our unknown theme. So when instrumentation is developed by either people who are custom white body spike weaving or big professional APM vendors, they always have to know ahead of time what they're going to measure. They always have to look for known unknowns. So we had a client, for example, who had an existing APM tool in their production system, and they had a performance problem. The problem was every 5 seconds, a certain HTTP endpoint that was used quite frequently would be very slow, as in it would slow down for like 2 seconds and do nothing every 5 seconds or so. Well, when we looked at the APM vendor's instrumentation approach, they were instrumenting the servlet request within this system, okay? And it didn't even show the pause that was going on. So the tool said, nope, there's no problem here. Everything's A-okay. But obviously, they had real customers who were frustrated by the performance problem on their website. So they needed to solve that problem. Now, the real cause that was going on here was that Tomcat had a resource cache. So that's like a cache of all the different HTTP resources that it has hooked up in the system. And it expired this cache in a configuration of 5 seconds. And one of those resources, when you said, hey, look, do you need to reload? Do you need to go and change anything and rebuild your resources? It would go off and scan the entire class path of the system to find out if there was anything else that had been added in there. You know, it's doing one of these like really smart dynamic reload things that you might find very useful in development, but would be an absolute nightmare in production. Now, the instrumentation-based approach that this tool vendor had used didn't spot that problem. And the reason they didn't spot that problem was because they were doing their instrumentation on the server request. They were blind to this kind of problem. They made an assumption that it was in a different area of the application, and so they didn't show the pause whatsoever. That's not the kind of thing that profiling comes into, because it's, you know, it doesn't make assumptions about where in your code base you get performance problems. And the other thing that I think is always really important to be thinking about when you're looking at different performance monitoring tools is the overhead they add to your system. It's no good having a system that looks like a fantastic Chinook, like some really fast flying, really effective plane going through the air, only for it to be carrying this huge weight and load around and slowing itself down. I mean, that applies to performance tooling. It can also apply to people using excessive logging in their systems as well. It's always worth understanding what's slowing down, and you want to make sure that your diagnostic information that's helping you solve performance problems isn't the cause of performance problems. Cool. But surely, we talked about all these different things. They're, very useful. Metrics is useful, offers actionable insight. All these things are useful to an extent. But isn't there a better way that we can think about solving these problems? And I think what we're going to talk about doing what we're going to talk about for the rest of this talk is about production profiling. So combining the idea of using metrics with production profiling in order to solve performance problems rather than with instrumentation. So let's take a look at production profiling. Well, firstly, let's say how we might want to use a production profiler in terms of a system. Well, if you've established that you've got a performance problem over a certain time period on some certain, I say apps, I mean, it could be different services and systems within your system. You want to query for that time period in those machines. You want to look at a type of information to profile. So we'll talk about CPU time and wall clock time as well. You could also memory profile in production as well. You want to view the results of what the dominant consumer of your resources. You want to know what is the bit of your code that's eating up the CPU time. What's the bottleneck to solve? Fix that bottleneck and deploy. So there's kind of an iterative process here. Look up a time period, find what's using the resource, fix it, deploy, and iterate. So I mentioned that there are different kinds of time that we can think about when we're looking at a system. One of those is CPU time, and one of those is wall clock time. So what's the distinction there? Well, CPU time is the time that your code is actually spending on the CPU, executing instructions, working away like a busy beaver. And wall clock time is the total time of an operation from the beginning to the end. So that would include time when it's on CPU, using up some CPU time, but it also could include time where it's waiting to be scheduled, where it's blocked on a lock, where it's waiting for data back from a hard disk on the machine, or even an external service on another system. Now, I like to think about the distinction between CPU time and wall clock time through the analogy of a coffee shop. Oh, maybe that's just because I'm addicted to coffee. Now, if you go to any good coffee shop or even a Starbucks, you'll see that they've got a big queue at the front of the coffee shop. And the wall clock time is a bit like the total time to get your coffee. It includes the time standing around waiting in the queue and the time on the other side where you're trying to figure out which of the bits of coffee the barista has put down is really yours versus somebody else who's waiting there. And the CPU time is much more like the time the barista spends actually making the coffee for you. Okay. And it's important to be able to distinguish between those two things because they can be useful in different contexts. CPU time is useful when you've got a lot of computational hotspots, bits of your code which are actually doing CPU work, finding inefficient algorithms. It's useful for those things because you might find in a system that you have times where your code is not executing, it's just been not scheduled on CPU because your system is doing too many things. Understanding the wall clock time is not going to help you improve the computational efficiency of your code, but using the CPU time is. On the other hand, you need wall clock for solving other kind of problems. A lot of performance problems aren't really CPU bottlenecked. Maybe they're blocking on an external I/O resource like a disk, or maybe there's a lock contention issue between multiple threads trying to use a Java mutex, like a synchronized block. Maybe you're waiting on an external system. And for those kind of problems, wall clock time can be invaluable for measuring what's going on. But Sadiq, there's a few different views that you can get for profiling code, aren't there?
Yes. So we'll start with the reports that you're used to getting from your kind of traditional desktop profiler, but that are available across the board. So hotspots. What are hotspots? Hotspots are the methods in your code that are spending most of their time. They are the methods in your code that are the dominant consumer of whatever the resource you're measuring is. So if you're measuring CPU time, then these are the methods that when we sample the program under test, these are the methods that that we see most as the ones that are actually running. And this report basically summarizes those. And you can often use that to try and work out what is actually consuming my CPU time or my blocking time or my memory allocation or such like.
Another view that profilers often provide is tree view. So tree view is basically taking all the methods in your program, building up this big tree where the parent node in the tree is the caller of the child node in the tree. So at the top of the tree in this example, we've got java-lang thread.run, and it's calling some task thread $wrapping runnable.run inside Tomcat, and down the chain we go to different methods being called from their parents. Tree views will often give you the self time, so the time within the method that itself is using up on the CPU, and the total time as well. So that's like the node and all of its children. So that can sometimes be helpful compared to a plain hotspots view for telling you what's calling your method when it's hot. Like if you've got a method that gets called in a bunch of different contexts, you want to know which one is the one that's making it hot. And then there's flame graphs. Flame graphs are the kind of exciting new kid on the block in terms of the profiling view. I mean, I think we had hotspots kind of visualizations for profilers back before we had GUIs, whereas flame graphs are an innovation by Brendan Gregg at Netflix. And the idea with the flame graph is, again, you're showing a caller-callee relationship. So they could go bottom up and look more flamey, or top down. This is a top down example. And in this kind of example, each parent is a caller of its child. So here we've got java-lang thread.run at the top, and then it's calling down the stack. Now, if you look at flame graph nodes, the self time that each node has is visualized by the difference between the width of a method itself, which each box is a method, and the width of its child. So we can see here this sun nio socket channel impl accept 0 method here is a lot wider than its immediate child. So it's spending a lot of time running that code. The width of each box is the total time. So the time for that method and all of its children to execute. So you can really kind of see with a flame graph a lot of the information that you would see with a tree view, but much more efficiently, much more compactly on screen. And you can see where the graph narrows down and where it ends up, but those are the things that are really eating up your time. But Sadiq, I've talked a bit about profiling and visualizations here. How do they work under the hood?
Sure. So now we're going to go over how profilers actually work, and specifically how they work in Java or the JVM. So let's start with the earliest of profilers, instrumenting profilers. So how does an instrumenting profiler work? Well, an instrumenting profiler adds instrumentation to the program under performance test in order to collect timings or information about the resource consumption of that program. So if you're trying to work out how much CPU time or how much walk clock time, for example, a program is using, you could an instrumenting profiler could instrument a program and add timing information to the start and end of every method, and then could use that to reconstruct how long the program was spending in every method that it was executing. The problem with instrumenting profilers is that in the act of instrumenting the program, they modify its behavior. And so in modifying the behavior of the program, the results are not accurate, essentially. And how it modifies the behavior depends on the type of program. So let's go back to the idea of the CPU time profiling, walk clock time profiling, where you are measuring at the start and at the end of a method. If you imagine a code base that is pretty horrific and has 1,000-line long methods and only a few of them, you could imagine that the overhead of instrumenting that is going to be far lower than instrumenting a nice, clean, refactored code base that has lots and lots of many small methods, right? Because the instrumentation code is going to be run far more frequently. So the overhead and how much it modifies the behavior of the program depends on the program under test. It's not like we can say it makes all programs 10% slower, so we'll just discount that from the results. And because of this behavior, it is very inaccurate. So it has high overhead and it's very inaccurate, not very useful. What else can we do? Well, the next step is sampling or statistical profilers. And how they work is they interrupt the application under performance test periodically based on the resource consumption that we're interested in. So if we were interested in walk clock time, and we could say interrupt the program every 100 milliseconds and say, what are you doing? And by what are you doing, we mean what is the stack that you're currently in? What state is the program currently in? So if we were doing this for this hypothetical program that we have in front of us, this diagram here, time runs on the x-axis. So we are calling web server thread run, which is then calling controller do something, and then repo.read person, and it's constructing a new person. So time is going along there, and the callies are in the bottom, and they callers at the bottom, and they call callies as you go up. So let's imagine this is a idealized sampling profiler. The green lines would indicate the point at which we interrupt the program and we grab whatever the method it's currently in, and the method it's in, and then what methods call that, etc., etc. So the first time we interrupt it, we'd interrupt it and we'd say, we're in web server thread run. The next time we'd interrupt it, we'd see, we're in the middle of a person constructor, which is called by read person, etc., etc. And we keep on doing this, and we record those samples, and then by aggregating them over a period of time, you end up with a statistical picture of the performance of the program. And you can do this for lots of different resources of interest, but unfortunately, this is a hypothetical, or this is a perfect implementation of a statistical profile. And as we'll see in a second, this gets slightly awkward to do in Java, and that has traditionally been the case. So let's wind back for a second to make sense of this slide. As I said earlier on, we use Java, and that normally means hotspot. Hotspot has a JIT compiler, so it has a microinterpreter, it has a JIT compiler. The JIT compiler will compile code on demand and apply a bunch of optimizations when it's doing so. And one of the optimizations that it relies on pretty aggressively is inlining, which is if you have a caller and it calls a callee, then it can actually inline the code from the callee, whatever method it's calling, into the caller. So let's remember that for a second. This, so the hotspot does inlining. The next issue is that Java and the implementation hotspot uses what are called save points. Now, save points are a mechanism by which hotspot can actually bring all application threads in the system to a halt in order to do some kind of work. So this could be the stop the world pause and say garbage collection. This could be bias lock revocation. There are a few things that are very difficult to do while the application is still running. So when we say a GC pause, what we actually mean is that we've hit a save point, the threads are parked, the GC is doing some work, and the threads then resume when that work is finished. Now, how are save points implemented? Well, save points are implemented by a read to a certain known memory location. And that read is done when the JIT compiler, it's done at the beginning and at the end of methods, and also inside certain types of loops where the JVM can reason that the loop actually terminates at some point. If the JVM can't determine that the loop terminates, then there are actually a save point in the tail edge of the loop. So we have save points that are added to this code. Inlining, and one of the big benefits of inlining is that we can inline code in methods that we're calling into the caller, and we can also remove the save points from it. Right? Now, why is this all useful? Well, The traditional method, and the easiest method of doing statistical profiling in Java, is to use a JVM method or a JVMTI method called getAllStackTraces. And that basically gives you all the stack traces for all the threads that are running in the system. Unfortunately, it requires all the threads to be at a safe point in order to do so, right? And the combination of inlining and safe point removal when inlining means that actually this ends up being quite inaccurate and also expensive to do. So let's go back to the diagram I've got in front of us. The purple entries on this diagram are things that the JIT compiler has determined are small enough that they can be inlined. There will be a performance benefit in inlining them. So it's inlined the new person constructor into read person and read person into controller do something. The light blue circles are safe points, right? They're at the beginning and at the end of methods and inside certain type of loops. So here they are at the beginning and the end of methods. Now, because getAllStackTraces requires all the threads to be at a safe point, just calling it periodically, which is what a lot of profilers do, is not an accurate way, or in fact, not a performant way of measuring, of profiling an application. So here's what would happen in this case here. We would say getAllStackTraces, and we'd basically we'd hit our first safe point inside web server thread run, and we'd say, okay, that's taking some time. Then we would trigger getAllStackTraces again, but we wouldn't actually get a sample until we hit the end of controller do something. Now, controller do something at the end of it is actually calling a few of these inline methods, which won't be attributed into the cost of the profile. So the problem is that in inlining and removing safe points, the naive or earlier methods of statistical profiling in Java can end up causing very inaccurate profiles and exhibits basically what's called the safe point bias, right? But there's another problem with safe points, which is if you trigger safe points very frequently, that is, if you profile at a fast enough rate, you can actually impede the performance of your system. So again, here is a hypothetical system. We have a bunch of threads. They have safe points in them. These little blue dots. The first thread maybe hits the end of a method and hits a safe point and is parked, right? The JVM actually triggers that by basically unmapping the memory location that a safe point is reads from, and so that triggers a fault, and then it's able to park the thread. So the first one actually is halted. The next one does so a little bit later, and then the next one does so a little bit later on. But the last one, maybe it has a loop, a so-called counted loop, where the JVM can reason that the loop does actually exit and doesn't need a safe point inside it. That might say not actually hit a safe point for quite a while. And so that time between the first thread and the last thread actually halting is wasted time. It's latency in your system, and it's actually wasted time when the system could be doing something useful. And if you're interested in actually how much that costs in your system, there's actually a JVM flag that you can use. This XX print safe point statistics will tell you the number of safe points and the time to safe point. How long am I waiting to actually hit a safe point? And because of this problem, we can't just call getAllStackTraces very frequently to get lots and lots of stack traces, because in doing so, we will impact the performance of the system. And we have the added problem that actually even the stack traces we're getting are not actually representative because they exhibit a bias towards safe points. So what do we do about that problem? Well, we need two ways. So when we talked about statistical profiling, there are two ways it works. Two ways it works. One, we interrupt the application under test, and then we need some way of sampling the resource of interest. So let's start with how do we interrupt the application. To interrupt the application, we can use signals. So signals are an operating system construct that your modern operating systems support, and they are a way of asynchronously delivering a message to a process or thread in the system. So you can say, I want to deliver this message to this particular process. And if you've ever used kill, if you've ever had an errant process running in your system and you want to kill it, you can, but when you say kill, you're actually sending a signal to that process. Now, we can use OS signals to interrupt the application that's under performance test. And when a signal is delivered to an application, it triggers what's called a signal handler. The signal handler is basically run as soon as the process receives the signal. Now, the problem with signal handlers is that they can be triggered at any point in the application's running. So they can be triggered in the middle of a memory allocation. They could be triggered while holding a mutex lock. So you have to be very, very careful what things that you do inside a signal handler. And there are only certain library functions that can actually be used inside a signal handler. And these are actually called async safe methods. And what's very convenient is the JVM actually gives us such an async safe method in something called async get call trace, which is a JVM method that basically gets the stack trace of the thread that we're currently running the signal handler in, the Java stack trace. So we have a safe way of getting the current state of the thread. And we can also, while we're in the signal handler, assuming as long as we're careful about not modifying anything and being aware that the actual Java application itself might be in an inconsistent state, we can also examine the JVM internals and pull for other types of resources. So it might be memory, it might be IO, that kind of thing. So there are ways we now have a way of interrupting an application. And then to sample the resource of interest, we can either use async get call trace to sample the stack. And depending on whether we deliver that signal for CPU time or wall clock, we can still measure that. Or we can examine the JVM internals to try and measure other resources of interest, like memory or disk IO or network IO or such like. So this slide basically summarizes that. OS signals are lightweight, and crucially, when an OS signal is delivered to a process, it's delivered to one thread. The rest of the threads in the application can continue running. It's only one thread where the signal handler is run, and actually ends up being quite lightweight and quite cheap. So, and then it's an approach that's not really used by existing profilers, things like Visual VM, existing desktop commercial alternatives that are designed to be run locally, don't use this method. It's come to kind of, it's really started to become popular the last few years, but you can actually have very low overheads. You can choose a reasonable sampling rate and have overheads that are almost immaterial in production. And there are open source profilers that indeed do this. Things like Honest Profiler, which is written by Richard here, Async Profiler and such like, use this approach. So if this kind of thing is if we can profile in production with very low overhead, then why don't people do it, basically? What we've discovered is that people are put off by practical reasons as much as technical reasons when they do these things. So a few of the kind of practical reasons that we encounter a lot with ad hoc production profiling. So ad hoc production profiling is, I've got a known performance problem. It's a known problem now, and I want to attach a production profiler to my servers and try and understand what's going on. For one, it generally requires access to production, right? And as we said earlier on, there are many environments where developers don't have access to production. It also involves manual work. You have to connect up to production, grab data, run reports on it, share those reports, and then iterate the process, like the how to use a production profiler slide earlier on that Richard went through. And also, as I said, the advanced statistical profiling, there are open source profilers out there, but these tend to lack the commercial support that people really want when they're actually connecting up things to their production servers. So that got us thinking, What if we profiled all the time? Would it get around some of these problems? Well, for one, you wouldn't need developers to have access to production, because if you just left a profiler hooked up to production all the time that was putting its results somewhere, then developers wouldn't need to actually have access to go in there or work with ops to try and get temporary access to a system, because it would continue. You would continually have the results, and once set up, you wouldn't need to have access again. It also, if you're profiling all the time, then it makes sense to invest in ways of actually processing that data you have in some kind of automatic manner. You can automate a lot of the manual work that you have. But also got us thinking, well, if you profile all the time, what else does it open up? So it starts opening up things like post hoc incident analysis, right? So you can come into work and say, well, look, our server cores pegged at 100% CPU last night for about 25 minutes at 3 o'clock in the morning. What happened? And with ad hoc production profiling, you can't do that because the system's hopefully back to normal by this point. You can't go backwards. But if you're profiling all the time, then you have access to that historical data. You can say, okay, things went wrong. Let's go and have a look at what the system was actually doing at that point in time. It also allows you to answer questions like, well, we've just pushed a new release to production and things have gone a bit squiffy, right? Our performance metrics are off. Well, what's the difference between this release and the previous one? Because you have a benchmark for what was normal. Whereas if you're doing ad hoc, well, you've already done a new release. It's very difficult now. You've got to roll back to go and look at what normal might have been before. And it then allows us to do other things like put the profiling data we have in context. So we talked about looking at performance regressions. Well, maybe we can attach other contextual information to samples, like what is the version of the application. Things like environmental parameters. What is the machine type? This is an Amazon C3 versus Amazon C4. And that then allows you to dice up your data and say, you know what, I'm only interested in our servers that are of this particular type. I want to understand, let's say, or I want to understand our JVM 8 versus JDK 11. Like, show me the difference in performance between the two and look at the reports for the two. Those are the kind of things that actually are very, very difficult to do with ad hoc profiling without lots of manual work. And so that's the kind of conclusion we came to a few years ago, and that's actually what motivated us to create Option, which we believe is a great platform. Option essentially is the JVM agent that uses the advanced statistical profiling that we talked about earlier on. You run the JVM agents on your servers, on your production servers. They gather results, and those are sent to our cloud environment or our on-prem environment. The aggregation service basically indexes those and aggregates them, and then there is a web-based reporting UI where users can then run reports against that data. So it's a way of basically applying continuous profiling in production, and it's a kind of complete package that does all of that for you. And we've had great kind of success with our customers in finding unknown unknowns or even tackling known unknowns with this platform. So in summary, it's possible to profile in production with low overhead. We went through some of the methods and some of the tools that you can use to do that. But really, we believe to get the best out of it, you need to profile all the time. Because by profiling all the time, you can get around a lot of the issues that you have with ad hoc production profiling, but also you can gain new capabilities from doing it all the time.
Great. Yes. Let's wrap up and conclude and just draw some threads together from this talk. We first of all said why performance mattered to you, why performance tooling mattered as well. It was about helping us solve specifically unknown unknowns, also known unknowns, but unknown unknowns that we couldn't think of in development time. Development and production environments were very different. They had different hardware, different software, and establishing a load in development environment that's representative of production is very hard, if not impossible. Metrics can be very useful for narrowing down problems, but they can also sometimes not give you an actionable insight. They can't necessarily tell you which bit of code to fix. Instrumentation has high overhead if you do it a lot, and also has a restriction that you need to know what to instrument ahead of time. Whereas continuous profiling can be very, very useful for developers, provides great insights and great approaches. We think strongly that we need a bit of an attitude shift on profiling and monitoring and change the way we think about things. We need to think about doing things in a systematic rather than an ad hoc way. So that's to say, being able to understand performance problems in as a methodology, as an approach that we can take, rather than just kind of doing those murder mystery style diagnostics where we kind of guess a little bit and hope for the best. We want to be proactive and not reactive about these kind of things, having the systems in place to measure and understand what performance problems happen in a production setting, rather than just reacting after the fact when something's gone wrong. That doesn't necessarily mean that you need to do premature optimization, but it does mean that if an opportunity for optimization arises, you need to be ready to understand what the implications of these changes are and know where to optimize. And to do those kind of things, we need to think about being continuous, measuring these things in production all the time. So they're not things that you just do when things go wrong. They're things that you measure all the time, so you're smooth, you're happy that they're always working, and they're just part of your natural rhythm, and you've always got that information, that historical data available. If you take one thing away from this talk, please let it be do production profiling all the time. As Sadiq mentioned, we were on the start of Opsian that has a great production profiling tool, but even if you don't want to use Opsian, please just do production profiling. You'll really benefit from it, and I'm sure you're going to love it. Great. That's the end of the talk, Elon. Thank you very much for hosting us. We're happy to take any questions if any of them have come in on Slack.
Yeah, thanks a lot for your talk. It was awesome. And thanks, Tenzing, for the questions on Slack. We have 3 questions.
Great.
They're more general, but yeah. So the first question is, how much deviation in performance are we talking here between development and production among Linux versions? Say, for example, Linux Ubuntu in dev and Red Hat in prod. Are we saying that if I profile a dev code, those numbers will be 50 to 100% different from that in production? Maybe on a single API call. Let's not talk about load here, assuming JVM versions being the same. So basically the difference between dev and production in different Linux versions.
Yeah, so different Linux versions, I don't know how big a difference you can get there. As I said, I know that there was a Windows update last year, so within the last year, where just that one version update had a 40% slowdown on UDP throughput. That's the biggest thing I've seen for a specific syscall. But I think there's also another aspect of this, which is, I mean, we mentioned hardware. And you might think of hardware as being something that influences the cost of operations like disk I/O, but it can also influence the cost of your Linux system call operations. So, for example, there was a big hoo-ha in 2017 when people were looking at the overhead of getting the current time, which is a thing that systems do all the time, right? And the syscall for getting the current time on AWS on Zen was about 70% slower than it was on an equivalent, or on a regular laptop machine at home. So even things like that, I know it's not quite Linux versions, but you get kind of cloud hosted versions can also cause big syscall overheads as well.
Okay, cool. And the next question, again from Tenzing, is also, is there an easy way we get proactive performance measuring during the dev build process, giving an indicator to the developers that they are maintaining SLO correctly under control before the code is run against business users' real-world data by QA team? So basically, yeah, to do this thing proactively in development to check whether we meet SLOs. SLAs maybe.
Yeah, I'm guessing it's SLAs. So I mean, it is possible to do extensive performance testing. I know people who do performance testing on their system, but the only people I know who do it well are people who do it, They invest huge resources into it. The only people I know who do it well have like a whole team of people dedicated to doing performance testing, because it's so hard to get right. You've got to understand the workload of your production system. You've got to make sure that you're hitting this, your whatever's doing the load test is doing the exact same thing that your users are doing in production. You've got to have the same you can see my face now. You've got to have the same like workload between different systems in production. You've got to have the same hitting of different endpoints. You've got to make sure your data distribution is the same. You've got to have the same configuration between databases. There's a lot of tools like, you know, Gatling, Apache JMeter, things like that for doing load tests. But it's not really a tooling problem. It's the fact that you basically have to spend a lot of engineering effort setting these things up, running them, validating them, maintaining them. As your system changes, they change. As you add new features and that change your usage pattern of your system, they change. It's a huge, it's not impossible, but it's a huge, huge effort for people to do. I would say for like 90+% of businesses, it just doesn't make sense to do it just because of the sheer cost.
And even if you have performance tests, it's still worth doing profiling on both your performance tests and your production environment, just to make sure that actually, are we exercising this code in the same way or even a similar way to production, right? Because if you're not, again, it might be the case that there's things that you're missing when you're doing this.
Okay, and I'll ask the last two questions from the chat because we should be over now. So, what would be an open source low overhead profiler, for example?
So we talked about some of them earlier on. There's things like Honest Profiler, which was written by Richard here. There's Async Profiler, which is similar.
Yeah,
they're both worth a look. It's worth pointing out that these are things that will let you do ad hoc production profiling. So you can hook them up to an existing, to an environment, but then the kind of the onus is on you to actually generate the results and that kind of thing. But yeah, there's also it's worth pointing out that in Java, if you're running the Java 11 or 12, there's also things like Flight Recorder and that kind of thing, which are now in the OpenJDK. But in the same way, it's still kind of an ad hoc thing.
Okay, and maybe the last question. Sorry, Nicola, but yeah, we are out of time. So the last question is from Carbo Limer, and it's basically connected to this one. What tools besides Opsian do you recommend for continuous profiling? We were using your kit for CPU sampling, and it was generating a lot of data. Is there an easy way to aggregate and monitor this data?
So as far as we're aware, I don't think there are any open source continuous profiling solutions. I mean, it's worth pointing out that there's actually quite a bit of complexity involved in Opsian to actually make this practical. We had to basically build our own data store to be able to actually index this data and aggregate it and stuff. And there's actually quite a bit of work involved in keeping this kind of thing running. So as far as we're aware, there's nothing out there that actually open source that does continuous production profiling.
Okay, then I think it's a wrap. Thank you again, Richard and Sadiq, for your talk, and thanks everyone who joined and who watched and who asked questions. And see you again next time.
see you. Bye.
Bye-bye.